Good morning, everyone. Also welcome from my side to the Additive Manufacturing Symposium. It's good to see so many faces back in real. We can have these face-to-face meetings. So today I'm going to talk about our recent activities in the field of additive manufacturing of iron-based shaped memory alloys. But before I start, also I want to say thank you to the many collaborators that we have here. This is truly a group effort spread over different sites. So we have a fairly big team at EMPA working on that type of alloys. We do have intensive collaboration with our colleagues from PSI who are also here today. And we have collaboration with partners from South Korea. They are also here at the conference. Professor Jin Lee from Busan National University, Dorian Kim from KeyTech. And the project has many sponsors, so it's one of the bigger projects that is running in our lab. Here's the outline. We'll explain you why we need these shaped memory alloys and then how we can print them, what we can do with those. And yeah, let's start with the motivation. So you might have heard of so 4D printed mechanical metamaterials. So metamaterials or mechanical metamaterials, those are, according to the definition that I found on Wikipedia, artificial structures with mechanical properties which are defined by their structure rather than by their composition. And so those can exhibit very interesting mechanical properties which cannot be found in nature. Such as these oxidic materials with, for example, negative Poisson ratio, metamaterials with very excellent damping capabilities for mechanical oscillations, or they have, as it is shown here, such hyperelastic or super stretchable properties, making them very interesting for various applications. And yeah, as you can easily see, because of their very complex geometries, they can often only be fabricated using additive manufacturing technologies. If you look up the literature, up until now, most of these metamaterials have been fabricated from polymers with fairly low mechanical strength. And the fabrication from metals has turned out to be challenging because it's very stiff, rigid material and it can often not really achieve these very interesting properties. So there is a class of materials, the shaped memory alloys. You might have certainly heard of those, which could be interesting for these metamaterials. So shaped memory alloys, let's start. That you have probably seen, or you probably have shaped memory alloys. So those can be these super elastic frames, glass frames that you can flex and they bend back, or you can really stretch them, then you throw them into hot water and they recover their shape. So very interesting properties. They have been known since the late 1950s, and there are different classes of these shaped memory alloys that have been investigated intensively, nickel titanium based, copper based, but also iron based shaped memory alloys. Additive manufacturing of shaped memory alloys has certainly been tried, and most of the literature focuses on nickel titanium alloys. So this, if you hear about shaped memory alloys, nickel titanium is often used as an equivalent for that. Samples with some super elasticity and shaped memory effect could be produced. However, additive manufacturing of nickel titanium is very challenging. So first of all, the material is rather prone to cracking, as you can see here. So you need to find a very sweet spot of the parameters. Then, so during additive manufacturing, the very high temperatures, you can evaporate one of the species, in particular nickel. And the problem there is that these shaped memory properties, they are constrained to very, very narrow compositional ranges. So if you're 0.1% atomic percent off, these transformation temperatures will be off by 10 degrees. And losing 0.1%, this can happen very easily. So here's the study, volumetric energy density, and here is finally the transformation temperature. So you can see it's difficult to really tailor the properties of the shaped memory alloys. But one of the biggest challenges here is the price. It's rather expensive. So this number I know because I ordered that powder, 5 kilos, for around 7,000 euros. So therefore it's used mainly for rather small and very specialized applications, mainly for biomedical components, so as these examples show over here. Okay, what else do we have? So let's go back to the table. Let's rule out the nickel titanium, copper, also difficult to process, but we have these iron-based shaped memory alloys. Let's have a closer look at those. So I just summarized 3 classes that have been intensively studied over the last couple of decades. So this first class, so the first one, there are no studies at all. The second one, that's an alloy that has been studied in Kassel by Thomas Niendorf's team. It's possible but difficult to manufacture. And then we have these iron manganese silicon-based alloys where we didn't have any studies on additive manufacturing. But we at EMPA, we really have plenty of experience with conventional manufacturing of these alloys. And yeah, just to summarize that, what we did. So I've been working with that material since 2007. We have developed and optimized such an alloy, which is now commercially used for civil engineering applications. So here's the nominal composition. Actually, there should be 5 silicon here. So with very interesting properties tailored for civil engineering applications as a self-pre-stressing rebar material. I will show you some applications afterwards. So the shaped memory effect in that type of alloy is the result of a mechanically induced transformation from austenite, gamma FCC, to the hexagonal type of martensite. And the reversion upon heating. So actually we do have a trip steel. It's a high manganese strip transformation induced plasticity steel. However, we have here a reversible trip effect, if you want to look at this. And here is a bit shown on the crystallographic range how that works. We create Shockley partial dislocations on every second plane, and that will just convert the FCC into the HCP lattice, so they are very close. Keep that in mind, we will need that later on. Just to show you what we have done with it, so there's the company Refair, which is a startup from EMPA, so you can buy that for retrofitting of buildings. So what is that? Well, actually that is a tunnel, but in one of the nicest places of Switzerland, reinforced in Jungfraujoch. But there are other applications, not only in Switzerland, but as you can see in different places, conventionally manufactured iron-shaped memory alloy, so hot rolled, forged material into rebars, into plates for pre-stressing applications. So therefore for us it was rather natural to ask the question, can we use the material for additive manufacturing? So we started that project together with our partners in South Korea. Because we had plenty of the material, it was also easy to ask them to atomize it, and we have 2 batches, one with and one without vanadium carbides. However, there are too many results, and so I mainly focus here on the SMA1 here, the one without vanadium carbides. We have 2 machines. That one is in my lab at EMPA. That one is the machine that is in South Korea that has been used. And we went into a standard parameter survey here, mainly changing laser power, scan velocity. We produced samples in vertical direction and horizontal direction, and then we also went into the testing. Having a look into the microstructure, we already found some interesting things. So first of all, It was fairly easy to print them with regard to porosity. So we have a wide range where we can really fabricate dense parts. But so here roughly, with the tendency, if we go to high scan velocities, so low volumetric energy densities, we saw occasional lack of fusion defects and very often these brittle cracks. With regard to the phases, we saw that we have a lot of BCC delta in the material with a very pronounced texture, and we have these very large and elongated grains as we know them from additive manufacturing. If we go to lower scan velocities, so we increase the volumetric energy densities, we could print high density defect-free parts, free of cracks, and we have a fully FCC microstructure with a pronounced 101 texture, and it's very fine and aqueous grains, which is a bit of counterintuitive at first, but if you look into that type of material, it becomes clear. So here again, low VED, we have high amounts of delta. At high VEDs, we have much higher amounts of gamma. Yeah, we have high manganese, austenitic stainless steels. Well, and those, they can solidify through the delta BCC if this criterion is fulfilled. So chrome equivalent, that's the ferrite stabilizers taken together. Nickel equivalent is the austenite stabilizers taken together. And this is empirically determined 1.5. So if we look at now the material, we have a ratio of 1.7. So it puts us on the delta BCC side, and therefore it's no surprise that we have that. So at high scan velocities, we just quench from the delta field. There is no time for any transformation. However, if we go to to lower scan velocities, so if we put more energy into it, so we slow down, well, the whole cooling. So we give it more time for the transformation, and therefore we see that, this very typical microstructure. So, of course, if we want to do that, something with it, it's good to get rid of this delta at first. That was IFR. So we went into also an extensive heat treatment study, and there you can see is at different temperatures. We fixed the time to 2 hours, so you can see that the delta transforms into the gamma. So we have a nice temperature at 800 degrees Celsius, where we could fully convert the BCC into FCC. And with that, we maintained also so from the 001, we can get a 101. And this is what we found out because we have really a close correlation orientation relationship between these two orientations in FCC and BCC, as we found out. Interesting, with regard to shape memory effect, we'll come back to that later, we also see very high stuck-in-fall densities that we create during the phase transformation. And fine and aqueous FCC gamma indicates that BCC delta to FCC phase transformation occurred by a combined displacive diffusion mechanism. So all in all, in comparison with conventionally manufactured material, this microstructure is fairly unique and explains later on also our behavior. Good, what we wanted to know, shape memory effect. So we did the most sophisticated experiments, as you can see here. Simply bending and heating it, that's the fastest you can do. And you can see in these bending tests we get fairly nice recovery, so here in real time. So it is a shape memory alloy after all. But of course we wanted to have a bit more understanding of the mechanical or the thermomechanical properties. And we tested, we've created samples in vertical and in horizontal direction. We did tensile tests, and we also measured really the shape memory performance. We elongated and we heated to 200 degrees, and we measured the recovered strain that we could get out. So what you can immediately see is that we do have a strong influence coming from the building direction. Horizontal samples show higher strength as you can see here, lower elongation and fracture. However, ductility is fairly good in the material. If we look into the shape memory properties, so the vertical samples, they exhibit a higher or a better shape memory effect than the horizontal samples. Here C, this means this is conventionally manufactured, hot-rolled material, so this rebar material, and we could see that we exceed the properties of the conventionally manufactured material. So why is that? Of course, it's the texture. That's a standard answer that you get on that. But now what does that mean? It's the texture. So we wanted to get a better understanding of that and went to PSI, in particular here to the neutron facilities, Poldi, and did experiments together with our colleagues there. In situ neutron diffraction allows you to do, to probe large material volumes, and we can look into the phase transformation behavior of individual grain families. Besides, we can learn really a bit more about the deformation behavior on a micro scale. And well, since the shape recovery is caused by this phase transformation, we had a look really at the gamma phase and at this epsilon phase. So this is a diffraction pattern that we could get there. So we have very large gamma. The epsilon is fairly small, already indicating that the amounts are not so high, and they are also fairly small in their geometries. So we did tensile tests, we interrupted those, did in situ, so did these measurements, and then we started evaluating the data. So first, what we looked into, that's the integrated intensities, first for the two phases, but as a function of the grain families. So we looked into, for example, 111, 200, 220, 311. And you can see that as a function of the applied strain, well, first of all, the intensity of the gamma peak decreases. So not surprising. This means it has to transform into something. It's no more gamma afterwards. And what you can also see, there is a very pronounced difference between the grain families. So we have here this 220, which shows apparently a very pronounced transformation, and we have other grain transformation which show no transformation at all, and starting to rotate and do some other things. Looking into our most pronounced epsilon peak as a function of the build direction, you could also see here that for the vertical direction, epsilon mountainside starts to form, or we could detect it at much lower strains than here for the horizontal. So here it's rather flat. It doesn't mean that it's not. It doesn't mean that it's not there. It's just difficult to detect because the peaks are small. But this mountainside transformation seems to start really at much higher stresses or much higher strains. Also looking into what we can also do is the micro strains in the material, also very convenient. Looking here at the two different grain families, so that's in very interesting behavior. So we know that the 220, that's the most active grain family, and we have in comparison here the 200. If we look at the behavior here, 220, so after an initial elastic deformation, the curve becomes flat. This is very interesting. This means we can apply a lot of strain, but there is no deformation happening in the grain. Or in other words, so if we look what's happening in the 200, so they have a overproportional increase in their slope. And this means, so here, in these grain families, we see transformation, or there is slip activity going on. And we have a load transfer from this 220 to the 200 grain families. So it's overall very complicated what is happening there in our material. Looking at the differences between vertical and horizontal, you can also see that here there's more activity in the vertical samples, because here the red curve is really flat, whereas the blue curve slightly increases. And here you see that the load transfer to the 200 is also much more pronounced. So in other words, more pronounced plastic deformation, more pronounced slip activity in the 220, and we have this load transfer. At a certain stress, the 200 can no longer withhold that. They also start to transform, and that's induced here. So going back to the shape memory effect, I mentioned it, we have this phase transformation. This is actually the result of the extension and overlap of stacking faults on every second 1-1-1 plane. And these stacking forms form due to the dissociation of perfect dislocations into partial dislocations. And we try to understand now what's the criterion, so for which grains are really active and which grains are not. And so we started to calculate the Schmidt factors. So Schmidt factors, so that's exactly this. Tau is, so here then we have cosine of this angle slip direction, angle slip plane normal. You can look that up in textbooks and start calculating for that, but we did that for the partial dislocations. And we made an interesting finding from in situ EBSD measurements. So here you see grains that are indexed, or with regard to our color scale below. And my PhD student, Irene, she calculated all the Schmidt factors. And what we could see here, we looked into certain grains. So where are we? So actually everything that is blue, so these grains. Here the Schmidt factor of the leading partial dislocation is always larger than the Schmidt factor of the trailing partial dislocation. And so this is consistent. And if we apply a stress on there, so we see the transformation there. Now what's happening, if we apply the stress, leading partial is larger, so the stacking faults that are already there, they become larger, they extend, they extend, they extend. And it's these stacking faults that are the precursors for this epsilon. And so if we have a lot of these stacking faults, so in our AM material we have more than in conventionally. If we have more fulfilling this criterion, then we will have more transformation, and that explains why we do have these orientational differences in our material. Okay, now is that good for something? Remember, we have a lot of BCC delta in our material, which in steels is usually considered to be detrimental for the mechanical properties. But we asked ourselves, could that be good for something? And maybe some of you remember our paper from, I think, 2018, where we played a bit with these high nitrogen steels, so selective evaporation of nitrogen and playing with phases in nitrogen. We had something similar in mind here. So here we looked into the influence of processing parameters on phase and microstructure formation. So here we use the second alloy, but this doesn't matter at all in this case. And we varied the laser scan velocities between 100 and 400. And what we can see at high scan velocity, not surprising, we have shallow melt pools, mainly FCC, 90%, and large and elongated grains with 001 texture. Low scan velocities, we get much deeper melt pools. We get this duplex FCC, BCC microstructure and very fine aqueous grains. Now what's happening here? First of all, also what we realized that we do have a pronounced evaporation of manganese as a function of the laser parameters. And that's actually something we hoped for. And you don't see error bars. It's because it's so reproducible. So it's not scattering, and this gives us some kind of control to vary the manganese content in our material. Okay, what's going on? How does this microstructure form? Well, I think we can say that the volumetric energy density, so our laser parameters, influence the melt pool size and the melt pool temperature. So at low VEDs, we have these shallow, small melt pools. High VEDs creates much deeper, much wider melt pools. with a much bigger surface area. The temperatures, we know, they can easily exceed 2000 degrees, go very high in the center, and we start evaporating manganese. Manganese is very volatile, it's known, and the evaporation, the amount of manganese that we're going to lose is a function of melt pool size and the melt pool lifetime. So here we lose less, here we lose more, and this can be controlled. So going back to what I explained before, we are somewhere on the brink between BCC and FCC solidifying material, and apparently we can switch between the two fields, depending on how much manganese we evaporate and depending on the cooling and solidification conditions. At 400 millimeter seconds of high scan velocities, we have a transformation directly into gamma, and that explains these large elongated grains. If we go through so at the lower scan velocities, we have delta forming first, and we have this solid state transformation into gamma and delta. And so it seems that laser particle fusion allows for controlled variation in phase fraction, grain size, and morphology, and also texture. Next question is, does this affect the thermomechanical properties? Shape memory effect? Yes, it does. So we checked that. Here are tensile tests. Here you see also this nonlinear behavior, which is known for the shape memory alloys. We have here, in this case, we have a very pronounced shape memory effect. So if we have that microstructure, we have much higher strength, but reduced shape memory effect. So and then now we started playing around, and this is just meant as a teaser. Because I already advertised that. So we could find out that we can control phase and grain microstructure through variation of the process parameters, but also during rescanning. So we can, on demand, make BCC areas or FCC areas, or by rescanning we can start writing into our material and play with the two phases. We can also later on heat treat that and create different grain microstructures. And I just want to advertise that. If you want to learn more about that, go to the talk of my PhD student, Irene Ferretto, tomorrow afternoon at 3 o'clock. She will explain exactly how she did these nice patterns. So much for that. Finally, we wanted to use the alloys and make some really nice examples here just to demonstrate that we do have the shape memory effect in 3D printed structures. Of course, this is not of any particular use, but you can imagine that we can make easily actuators from the material, 3D printed actuators. So our colleagues in South Korea, they also printed this spider type of material, which after activation can, for example, lift certain weights, also act as an actuator. We can make these metamaterials. So here are several examples for 2D metamaterials which are supposed to have negative Poisson ratios. We can easily print them, and we could show that we can maintain this negative Poisson ratio effect. Actually, those are meant for compression, but our colleagues, they did also tensile tests, and yeah, we see it ruptures. Doesn't matter, just go there also with the heat gun, and then you don't see the defect anymore after it's fractured. So it's a nice material. Of course, it doesn't have the load bearing capabilities anymore. But yeah, so we can make these metamaterials. We went also into the fabrication of more complex 3D lattice type of structures, which are of course lightweight because there is not much material. And with the geometry, we can tune, for example, Young's modulus. But with these structures, we can amplify the shape memory properties. So, for example, this pseudoelasticity can be enhanced by a clever design of the lattice structures, which we could show here. And what is also interesting, these lattice structures, even if they have been deformed, of course not to very, very high strains, but if they have been deformed, we can heat them and they will recover their shape afterwards. That's the final for what we did. This is going into metamaterials for seismic applications or for damping applications, in collaboration with our civil engineers. So the idea was here to make such snap-through type of structures where we have also negative stiffnesses. So once you exceed a certain threshold stress, these struts start to, well, snap through, just go on the other side. And with that type of design, you can actually dissipate a lot of mechanical energy in the material. So if we load and unload, so you see there is a large hysteresis here, and that is energy that you have in between. So that was the theory, and yeah, we printed that 2.5D structure, precisely speaking, and we tested it. And we could see, yes, it is there. We tested it against, for example, titanium and steel. And the shape memory part is much superior because of this shape memory, because of this inherent pseudoelastic properties. So now this is already an outlook. This is what comes next. Now we really want to study more complex structures, really more structures where that you can really only fabricate using additive manufacturing. And this is a bit where we are right now. And I think it offers really many, many interesting possibilities. So just to wrap this up, so the EMPA alloy that has been around for some time could be successfully fabricated using laser powder bed fusion. We saw that the shape memory properties are superior to those of conventionally manufactured alloy because of this very unique microstructure that we get, which we could find out in our detailed studies. And the special solidification behavior and phase transformation behavior, it allows us, well, to play with the microstructure. So it's not random. Apparently we can control that. We have nice possibilities which we have to further investigate. More about that tomorrow. And so now we're printing 3D parts, metamaterials, actuators, clamps, fasteners, so there are other projects going on. And if you know more, if you have new ideas for what to do with it, just come and we can discuss also that. With that, I'm at the end of my talk and open for questions.